analytics techniques using Excel, linear regression. So what we're about to do now is explore linear regression on a data set to first be able to understand how it can be used for forecasting as well as relationship modeling, and second, to understand some of Excel's powerful functions that let us do this fairly easily. Now before we get into that, let's talk about regression. Now for those of you who have wandered into familiar territory and have worked with regressions before, this should be fairly simple. If not, let's quickly discuss the concept and address exactly what we're trying to do here. Right. So how often have you heard sentences like this, or how often have you heard people say sentences like this, especially confident people, right? So maybe a car salesman who says, "We usually sell more cars during our promotional periods." Or a sports analyst who says, "Every time Sachin Tendulkar is in form, India wins, and I can guarantee it." Or maybe an ice cream store owner who says, "Our ice cream sales always spikes when it's hot outside." Now while these are great statements to make and may or may not display someone's experiential notions regarding something, maybe a domain or a specific business, they're still not specific statements enough, especially from an analytics standpoint. Furthermore, they may not even be correct. I mean, how often do you encounter someone who makes a confident statement like that, but when you actually look at the data, it doesn't really add up. If we break these statements down, they're essentially describing relationships between certain variables. More promos, more car sales. More runs by Sachin Tendulkar, India wins. A hotter day, more ice cream sales, and so on. Now, a regression analysis is basically a method to mathematically model and understand the impact of one or more variables on another variable. It's a way of putting a number against it and quantifying that very relationship, because in the world of analytics, as you know, we need to know just how impactful that relationship is if we are to use it in a model. If it's indeed true that Sachin Tendulkar's good form boosts India's chances of winning, then a regression analysis can help us understand exactly how much. For example, it can tell us that with each additional run that Sachin Tendulkar scores, the probability of India winning goes up by, say, 2.5%, or something that specific. On the flip side, it also helps us understand if there are certain variables and relationships that we can ignore, if an assumption that we previously made is incorrect. Maybe certain variables that we thought had an impact on another variable, but in reality has no mathematical impact at all. Now let's look at some examples of relationships between variables that I've plotted here. Now the first graph you see here is basically a scatter plot showing the relationship between two variables, x and y. Right? Now just by looking at the graph, we can already spot a clear relationship between the two. As x increases, y is also increasing, and it seems to increase with it in corresponding fashion. It's almost in equal proportion. Now let's do something, right? Now this is simple enough. Let's now plot a trend line and mathematically represent this relationship. So what I'm going to do is click on the data series here, right click, and say add trend line, and I'm going to ask Excel to plot a linear trend line for me, right? As you can see, Excel has plotted a little line here that passes through all of these graphs, and now I'm going to say display equation and display r squared. Now let's get this out of the way. Let's move this somewhere where it's more readable, right? So as we can see here, this trend line that we just plotted almost perfectly represents the average relationship between the two variables. Now obviously not all the points on the scatter plot fall exactly on the line, but on average it would be fair to say that this line is a really good representation of the relationship between x and y for this particular data set. Right? Now here, since we asked Excel to also plot and show us the equation, a linear equation here that we see tells us more about this relationship, right? So it says y is equal to 0.9926x plus 0.4872. So there seems to be an intercept, and then you have the slope. Now linear regression equations are usually of the form y is equal to ax plus b, as we can see here, or y is equal to a plus b1 x1 plus b2 x2 and so on if there are multiple independent variables. Now in this case, y is what's called the dependent variable, right? Because it depends on the value of x. As x increases, y increases, and so we can use x as a driving factor. So y is the dependent variable and x here is the independent variable. So we've modeled and now know the equation that can tell us what the value of y will be for any possible value of x, even one that's outside the range of this particular graph, for example, right? So and that can be used for forecasting the value of y for future values of x that we might know of, because x is the independent variable. So this right here is your first example of conducting a linear regression. Since we have only one independent variable, which is x, this here is referred to as a simple linear regression, right, which has only one variable. In real world business cases, it's a lot more common to see multiple independent variables that drive the dependent variable. We'll look at an example of that in a few minutes and see exactly how Excel can help us solve it. So in our current equation, if it's of the form y is equal to a plus bx or ax plus b, in this case let's say it's y is equal to ax plus b, then a is 0.9926x and b is 0.4872, right? In more popular convention, it's usually represented as y is equal to a plus bx, in which case a would be the intercept and b would be the slope, but that's just semantics. Now I'm going to ask you a tricky question. How do we know that this is the right line? How do we know that our regression parameters and the equation here are good enough to predict a future set of observations accurately? Now this is where we typically apply a few tests known as goodness of fit tests, which essentially tell us how well a model fits a given set of data. In a simple linear regression like what we have here, it's easy to eyeball the line and understand how good the fit is. But that may not be possible once you have a pattern that's not this clear, or once you have multiple variables and you're not able to plot it on a simple two-dimensional graph. The first test is by studying residuals, right? So as you can see here, like we talked about earlier, not every point sits perfectly on the graph, right? Which means if we were to study the difference between these points in this example, right? So basically the distance between every single actual point and the corresponding point on the graph for that value of x, and that would give us the residual. So residuals are basically the difference between actual values and predicted values of y for a given value of x. Now it's important that these residuals be small, and especially in relation to as a percentage of the actual value of y. It's also important that there be no pattern to the residuals, right? So you always want the residuals to be random and unpredictable. Now if we find that the residuals are skewed in a particular direction, or there's a pattern where the residuals are always increasing with increasing values of x, for example, then we have a problem. Now the second test, or the second goodness of fit, it's a tongue twister, sorry. The second goodness of fit test is called R squared. So as we can see here, we also asked Excel when we plotted the trend line to give us the value of R square, which in this case is 0.98. Now R square is one of the most common methods, in my experience, of measuring how well a model fits. There's a mathematical formulation of R square, but I won't get into it here. But basically, it is a representation of the proportion of variance that is explained by the independent variables. Right. So it's basically computed by using the residuals when x is taken into account, as opposed to when it's not. So to put it really, really simply, does x matter at all to y? That's the question it's trying to answer. Now R squared typically takes a value between 0 and 1. If R squared is equal to 1, it means the model is a perfect fit. And if it's 0 or close to 0, it means there is no fit at all or almost no fit. So the higher the value of R square, the better the fit is. So in this case, R square is 0.98, which means it's a great fit, which is something we can already see on the graph visually because it's a very simple example. There are a few other ways to measure the goodness of fit, like adjusted R square or chi-square. I'll leave them to your independent research. But once you understand the concept of what you're trying to do here, which is basically model how good the fit is, then you'll easily be able to understand those concepts. But fundamentally, prep the data, build the model, and test the fit. So in a Johnny Cochran sort of way, if it doesn't fit, you mustn't use it. I apologize for that terrible joke, but I've recently been watching a TV show called The People vs. O.J. Simpson, so it's fresh in my mind. So now then, let's look at these other graphs right here and try the same thing. And then let's work on a quick example of a linear regression with multiple variables.